Hello everyone. For my last few tutorials, I like to talk about surface integrals. But before I do it, I have to talk about curl and divergence first, as well as parametric surfaces, or surfaces given by parametric equations, as they will crop up when we start computing surface integrals, as well as special theorems related to them. So in this video, I like to talk about curl and divergence first, which are special properties of a vector field. If we have a vector field given in the notation we are familiar with, then the formal definition of curl is third component with respect to y minus second component with respect to z times the x-coordinate or first component of the vector plus first component with respect to z minus third component with respect to x times the y component j of the vector field plus second component with respect to x minus first component with respect to y times the z component of the vector field k. This may seem like a lot to remember, and it seems to come out of nowhere, but we can use something that is logically easier to remember if we do. First remembering what the gradient vector field is, and then using the definition of the cross product we found earlier to state the curl is exactly equal to the cross product of the gradient vector field with the normal vector field, where I mean normal here meaning traditional or usual, rather than the specialized definition of perpendicular. So now that we have a more simpler definition of curl, in terms of how easy it is to memorize, then we can state if the vector field has continuous second-order partial derivatives, the curl is always equal to 0, provided you are taking the curl of the gradient vector and not the normal vector, which should be easy to verify if you remember how partial derivatives work. We can next state that if a vector field is conservative, its curl is always equal to 0, because one definition of a conservative vector field involves a gradient. And we saw just before this, the curl of the gradient is 0. So this means we can test if vector fields are conservative using the curl and the cross product definition. As in this example, we compute the partial derivatives and specify what the p, q, and r components are for the vector field. We then do the computation using the determinant of a 3x3 matrix. And we see, fortunately for us, the final answer is 0, so we have conclusive evidence that the vector field is conservative. We would next like to define the divergence of a vector field, which is the dot product of the gradient and the vector field rather than the cross product. But it is similar otherwise. And we know that the algebraic definition of the dot product is first component of vector 1 times first component of vector 2 plus second component of vector 1 times second component of vector 2, and so on. So if we were given this vector field and told to compute its divergence, we would simply multiply all of the partial derivative components by the vector field components and then compute them as if we are asked to find the partial derivatives of the components, and then simply add all these results because of how a dot product works. So we get a final answer after we simplify our work of 2 times x times y plus x times z. There's actually a special rule that relates divergence and curl, which is that the divergence of the curl of a vector field is always 0. So if we are given a specific vector field, we can verify this is true by first doing the cross product for the curl, and then take the divergence of this result, and we see we get a final answer of 2z minus 2z equals 0. And a way to understand why this works for all vector fields is that the curl represents how quickly a vector field turns, because of what curl means outside of mathematics, and the divergence represents how random or deviant the vector field is from the path indicated by the curl, as you should probably guess if you know what divergent means in other contexts such as the humanities. Now that we have figured out how curl and divergence works for vector fields, we can talk about 3D surfaces given by parametric equations in the next video. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.